All right, so I want to continue down this quantum rabbit hole for quantum information, and now I'm looking a little bit at trapped ions. So let's see what Professor Nano has to say about trapped
Quantum
ions.
computing is sparking imaginations around the world, with the
Wow.
potential to solve problems that even the most advanced classical supercomputers can't handle.
Okay.
Today, we're diving into one of the most fascinating and promising quantum computing platforms,
Mm-hmm.
trapped ions computing.
Mm-hmm.
If you've been following recent developments, you might have heard about IonQ. This company has been making waves with a valuation of around $9 billion.
Okay.
There's also Quantinuum, born
Mm-hmm.
from the merger of Cambridge Quantum and Honeywell Quantum Solutions, leading the charge in this exciting field.
Okay.
So why are these companies, along with many others, betting big on trapped ion technology? What
Because
makes it stand out as a platform
that's all
for
they
building
know.
quantum computers? In the next 20-ish minutes, we'll explore the fundamental physics behind trapped ions and find out
Mm-hmm.
why they could hold the key to the future of computing. The basic idea is simple yet
Yeah, it's just everything is a sales pitch nowadays. But I'm gonna fast forward through this.
brilliant. Trapped ion quantum computers use ions, atoms that have either gained or lost electrons, confined within electromagnetic traps.
Mm-hmm.
These ions are suspended in space, isolated from their environment, allowing us to
Right.
exploit their quantum properties with incredible precision.
Okay.
The surrounding environment can be a quantum computer's worst enemy.
Mm-hmm.
It introduces a phenomenon known as decoherence, where the quantum
Right.
state of the ions gradually loses its quantum properties due to unwanted interactions with the outside world.
That's correct.
To counter this, trapped ions are confined using devices called Paul traps, which we've explored in more detail in a separate video. Paul traps work by
Mm-hmm.
combining static and oscillating electric fields to keep the ions suspended in space, isolated from environmental disturbances.
Mm-hmm.
But that's not all. These traps don't just hold the ions in place, they can also move them with incredible precision, shuttling them between different zones for computation. For example, Quantinuum's H-series
Mm-hmm.
quantum computers use this very technique to manage 56 physical qubits, enabling an impressive all-to-all connectivity that's essential for complex quantum operations. In this video, we'll start by exploring how the internal properties of trapped ions can be used to create different types of qubits, specifically optical qubits and hyperfine qubits. Next, we'll introduce the quantum computational space. This is the mathematical framework that describes the system, including both the qubit states and the collective phonon modes, the quantized vibrations of the ions. These phonon modes play an essential role, as they can be manipulated with laser pulses of various colors. This enables critical operations like the C-NOT gate and entanglement gates, which are fundamental for quantum information transfer and creating entanglement between qubits. We'll also show how these phonon modes can be harnessed to cool these ions to their motional ground state, using a technique known as sideband cooling. This step is crucial for achieving the precision required in quantum computations. Finally, we'll break down how qubit-specific operations are performed, everything from initializing the qubits to encoding quantum states and reading out results. Let's begin. Chapter 1. Optical qubit versus hyperfine qubit. A variety of ions are employed by different companies and research groups for their trapped ion quantum computers, each chosen for its unique advantages.
Mm-hmm.
For example, IonQ and Quantinuum are well known for its use of barium and ytterbium ions. In this video, however, we'll focus on one of the most widely studied examples in the literature, the calcium ion. A neutral calcium atom has 20 electrons, but when one electron is removed, it becomes a positively charged calcium ion.
Okay.
This ionization process is essential because the resulting charge allows the ions to be confined and manipulated using electromagnetic fields. These fields form the foundation of precision control in trapped ion quantum computing, as charged ions are much easier to trap, move, and address individually.
Ionizing the atom, Doppler cooling, Earnshaw's theorem. We're not sure what that is. Paul trap and Mathau equations, ion lattice formation. Okay, so essentially Doppler cooling is you tune the laser so that the atom only is resonant, the excitation of the atom is only resonant with the laser when it's headed in the direction, when it's going against the laser. So that way when it gets a kick, it's always against its speed of motion. But if it's going the other way around, it's, I guess, blue shifted, red shifted. That's sort of going away from. Anyway, so it's should be red shifted, but blue shifted, I guess. This is saying blue shifted, but I guess it's red shifted. So you would not see the essentially the laser would be transparent when the atom is when the ion is moving away from the laser. So as it goes back and forth, it only has a potential to, on average, lose momentum.
Again, please check out the video on this topic in the same playlist. The structure of calcium's electrons is determined by the well-known Pauling diagram, which organizes electrons into specific shells and orbitals. The numbers indicate the principal quantum number, representing the electron shell, while the letters denote the type of orbital.
Right, so this is the first First shell, 1. S2, it's been a while, but can only be in the configuration S. 2, why is it 2? 2 because it can only support 2 electrons. I don't think that's the spin. It's been a while, I should look this up. This is the second shell, the s orbital and the p orbital. So the s orbital can support 2 electrons, the p orbital can support 6 electrons, and in total they have 8 electrons. This is the third shell, again s and p, and then in the fourth shell, because you've kicked one of the electrons out, there's only 1 electron in the s orbital.
Each electron is associated with a specific energy level, which can be described mathematically using quantum numbers. For quantum computing, 2 energy levels of the calcium ion are typically selected to represent the qubit states.
Optical qubit with a trapped ion. So this is hyperfine splitting, or let's see what they have to say.
A ground state denoted as 0 ket, and an excited state denoted as 1 ket. When these atomic orbitals are used as qubit states, we call this an optical qubit. Why the term optical? It's because the energy difference between these levels corresponds to a frequency range of 400 to 790 terahertz, which lies in the visible part of the electromagnetic spectrum.
Okay.
This choice has significant advantages. The large energy gap associated with visible light makes optical qubits less susceptible to certain types of noise. Moreover, these transitions can be precisely addressed using focused laser beams, enabling high levels of control during quantum computations. However, there are other kinds of qubits beside the optical qubits. The degeneracy of energy levels with the same principal quantum number in an atom can be broken when the nucleus has a non-zero magnetic dipole moment caused by the spins of protons and neutrons. This results in an interaction between the nucleus spin and the spin of the outer shell electron, known as magnetic dipole coupling. Take the hydrogen atom as an example. With just 1 proton and 1 electron, the system has 4 possible spin combinations.
Right.
The proton can be spin up or spin down, and the electron can also be spin up or spin down. When this interaction is considered, the rotational symmetry of the system is broken, and the degeneracy is lifted. This leads to hyperfine splitting, where energy levels split into distinct states. For more details on how degeneracies are associated with symmetries, the viewer can read Chapter 17 of Feynman's Lectures on Physics, Volume 3. For instance, the hydrogen atom's ground state splits into 2 levels. The lowest energy state, known as the singlet state, is a combination of opposite proton and electron spins. And its antisymmetric nature means the wave function changes sign when the spins are swapped. The first excited level contains 3 possible states, called the triplet states, where the spins are either aligned or form a symmetric combination. This is called the triplet state because it is threefold degenerate. Hyperfine splitting creates transitions that typically occur in the microwave range, with frequencies often in the order of tens of gigahertz to a terahertz. These transitions are much lower in energy compared to optical qubits, whose transitions occur in the hundreds of terahertz range. However, this lower energy means hyperfine qubits have much longer coherence times. Thanks to the Heisenberg uncertainty principle, a smaller energy difference corresponds to a longer state lifetime. Experimentally, hyperfine...
If the uncertainty in energy is small, the uncertainty in time is large, because it's greater than or equal to okay, yeah.
Fine qubits can maintain coherence for over 10 minutes, compared to around 1 second for optical qubits. The trade-off, however, is that the longer wavelengths in the microwave range make it more challenging to address individual ions precisely. Despite this, both hyperfine and optical qubits are actively studied in leading ion trap labs, as each offers unique advantages for building scalable quantum systems. Chapter 2. Computation with trapped ion qubits. As we've discussed in previous videos, a qubit is a physical system with 2 distinct states, often represented as 0 ket and 1 ket, corresponding to 2 well-defined energy levels. These states form the foundation of quantum computation. With them, we can create quantum superposition, where the qubit exists in a blend of both states, or achieve entanglement between multiple qubits, which is essential for unlocking the power of quantum algorithms. Now, imagine a linear chain of ions confined within a Paul trap. This clever device uses static and oscillating electric fields to hold the ions in place.
Static and oscillating fields. Static field and an oscillating field.
The ions are isolated in a vacuum, reducing unwanted interactions with the environment. This isolation is one of the key reasons why trapped ion systems have such long coherence times. They minimize the effects of decoherence, preserving their quantum properties. Let's focus on a Paul trap containing 4 ions, which we'll label as qubits 1, 2, 3, and 4. Each qubit has a ground state, represented as G ket, and an excited state, represented as E ket. Using focused laser beams, we can address individual qubits, inducing transitions or creating superpositions between these G ket and E ket states. When the laser frequency matches the exact energy difference between the ground and excited states, this is called a carrier transition. We denote such resonant carrier transition between electronic states with a green laser. When multiple qubits are involved, the quantum state of the entire system is described using the tensor product of the individual qubit states. This mathematical framework allows us to model the full complexity of a quantum system, paving the way for operations like entanglement and multi-qubit gates. Because the ions share a single electromagnetic potential, their motion becomes quantized into what we call Phonon modes. You can think of these modes as vibrational states that can be either excited or de-excited. Phonon modes can be excited in 2 ways, either by using detuned lasers, where the laser frequency is slightly offset from the electronic transition, or through thermal energy from the surrounding environment. Thus, in addition to the electronic states of each ion, the total physical Hilbert space of the system also includes the states of these quantized Phonon modes. We represent these phonon states as n sub p ket, where n sub p denotes the number of phonons. These phonon modes are incredibly important because they act as a bus qubit, enabling interaction between different ions in the system. Essentially, they serve as a bridge for quantum information to travel across the ions chain. Now, let's take a closer look at the computations we can perform with a single qubit in this composite Hilbert space, which combines both electronic and phonon modes. For simplicity, let's consider qubit 1. The Hilbert space of qubit 1 includes a hierarchy of states. Each electronic state, G ket or E ket, can exist in combination with different phonon modes 0p, 1p, 2p, and so on.
Here in California, we have lots of...
These ads are killing me.
To keep things manageable, let's focus only on the 3 lowest phonon modes. In this setup, the phonon modes are equidistant in energy, meaning the energy difference between each mode is the same. This separation is given by the quantized amount h bar omega p, where omega p is the phonon frequency. This regular spacing is key to manipulating the system with precision, as we can selectively address these transitions using carefully tuned laser pulses. Now, let's focus on how we can manipulate qubit 1 using a green laser. When the laser frequency matches the energy difference between the electronic ground and excited states, the qubit undergoes a carrier transition, moving between G ket and E ket. The hierarchy of electronic states that will undergo the carrier transition will depend on the state of the phonon mode as shown. In other words, the phonon state is conserved in carrier transition. However, things get more interesting when the laser frequency is slightly detuned from the electronic resonance, specifically by an amount equal to a vibrational quantum. If the laser frequency is increased by the vibrational quantum, we induce a sideband transition where the ion's electronic state is excited, while simultaneously adding energy to the vibrational mode. Since its energy is slightly larger than the green laser, we denote this as the blue sideband transition. On the other hand, if the laser frequency is decreased by a vibrational quantum, we induce a red sideband transition, where the electronic state is excited while losing energy from the vibrational mode. These phonon sideband transitions are crucial for manipulating the quantum states of trapped ions, as they allow us to couple the ion's electronic states with its vibrational modes. To see this in action, let's extend the example to 2 qubits, labeled as qubit 2 and qubit 3. Each qubit's physical Hilbert space consists of a hierarchy of electronic states G ket and E ket paired with different phonon modes 0p, 1p, 2p, and so on. However, the computational Hilbert space, the part we actually use for quantum computing, is much smaller, typically limited to the electronic states and the first 2 phonon modes 0p ket and 1p ket. Here's the key idea: the collective phonon mode acts as a bus qubit, mediating interactions between the electronic states of different ions. For example, if the phonon bus qubit starts in the ground state, both qubit 2 and qubit 3 will be in their lowest hierarchy electronic states. Now, let's focus on qubit 3 and examine what happens during various laser-driven transitions. When the red laser is applied, it lowers the electronic state, while the blue laser raises it. For our purpose, it is sufficient to just remember that the red laser induced lowering of the electronic state. Worth repeating again, the red laser induces lowering of the electronic state when the phonon bus qubit is at 0p ket. Importantly, the behavior of these transitions depends on the state of the phonon qubit. If we flip the phonon qubit from 0p ket to 1p ket, the roles of the red and blue lasers switch. The red laser now raises the electronic state, while the blue laser lowers it. This is exactly how qubits communicate with one another. The red laser can raise or lower the electronic state of a qubit, and the action depends entirely on whether the phonon bus qubit is in its ground state or excited state. It's almost magical when you think about it. This ability to control which way transitions through the shared phonon bus qubit is the foundation for implementing universal quantum gates, such as the C0 gate and entanglement gates. By carefully combining carrier and sideband transitions, we can precisely manipulate both the electronic states of individual ion and the collective vibrational state of the chain. This interplay between electronic and vibrational states is the building block for multi-qubit operations, which are essential for quantum computation. In future videos, we'll dive deeper into how gates like the C0 and entanglement gates are realized in trapped ion systems. Chapter 3. Sideband cooling of qubits. We've already seen how the phonon qubit plays a vital role in mediating interactions between the internal electronic states of different ions. To ensure high-fidelity quantum operations, it's crucial that the ions start in a low phonon state, ideally their vibrational ground state. Any excess motion introduces noise, reduces gate fidelity, and can lead to errors during quantum computations. This is why cooling the trapped ion to their motional ground state is a critical step in quantum computing. Let's revisit the Hilbert space of a trapped ion. Beyond the electronic levels, the ion also has a hierarchy of equally spaced vibrational modes, labeled as 0p ket, 1p ket, 2p ket, and so on. The physical Hilbert space is therefore much larger, encompassing both the electronic states and these phonon sidebands, as we discussed earlier. These phonon sidebands represent the quantized motion of the ions within the trap and form an additional set of states that interact with the electronic levels. When the phonon is in the 0p ket, we are at the motional ground state. To cool the ions, we use a technique called sideband cooling, which allows ions to be cooled down to their motional ground state. Sideband cooling is a game changer because it prepares trapped ions in a clean, low-noise state, setting the stage for high-precision quantum operations. This precision is one of the reasons why trapped ion qubits can achieve such high gate fidelities in laboratory experiments, making them a standout platform in the quantum computing world. Let's imagine a ground state electron occupying the following vibrational state. The basic idea is to drive the trapped ion using a red detuned laser, inducing a red sideband transition. This transition excites the trapped ion to a higher electronic state, while simultaneously reducing the phonon number by 1. Once in the excited state, it spontaneously emits a photon, decaying back to the ground electronic state. Importantly, during this decay, the ion has a high probability of remaining in a lower vibrational state. By repeating this process, the vibrational energy or phonon quanta is gradually pumped out of the system until the ions predominantly occupy their motional ground state. Chapter 4. Qubit encoding, initialization, and readout. So far, we've discussed the basics of encoding qubits as 0 ket and 1 ket, but what exactly are the physical states within a calcium ion that represent this information? Let's break it down. In a calcium ion, the relevant states are specific atomic orbitals. When the trapped ion is in its ground state, its highest energy electron resides in the 4s orbital, which we use to represent the 0 ket state. The 1 ket state, on the other hand, is encoded in the 3d5 halves orbital, which is the first excited state. Additionally, the 4p1/2 orbital serves as an auxiliary state for cooling and initialization, a process we'll dive into shortly. This choice of qubit states is deliberate. The transition between the 4s and 3d5 halves orbitals is dipole forbidden, meaning it is highly unlikely to occur spontaneously. This ensures that the quantum states are long-lived, making them ideal for quantum computations. By contrast, transitions to the 4p half state, such as the one between the 4s and 4p half orbitals at 393 nanometers, are dipole allowed and occur very quickly, with a lifetime of just 7 nanoseconds. Instead, the transition between 3d5 halves and 4p1 half at 854 nanometers has a slightly longer lifetime of 101 nanoseconds. For comparison, the dipole forbidden transition has a much longer lifetime on the order of 1 second at a wavelength of 729 nanometers. This longevity is a key factor in ensuring the stability and coherence of the qubit quantum states. A quick side note. These contrasting lifetimes are determined by selection rules, which govern the likelihood of transitions. Electric dipole transitions are the most probable, while higher order transitions, such as quadrupole or magnetic dipole transitions, have stricter rules and are much less common. Now, before any computation begins, the trapped ion qubits must be initialized. Initialization is critical because it ensures that all qubits start in a well-defined, reliable state, providing a solid baseline for quantum computations. Earlier, we discussed how the fun and bus qubit is initialized through sideband cooling. Now, let's focus on how the electronic qubit states are initialized. Here, we show how to initialize the electronic qubit state to their common ground state, the zero ket, in calcium ions. Initialization is achieved using a process called optical pumping. This technique depopulates the 1 ket state by driving it to an auxiliary state, which then decays preferentially to the 0 ket state.
Right.
Repeating this process a few times ensures that the entire system is reset to the well-defined 0 ket state for all qubits, making it ready for quantum operations. Finally, let's talk about how we read out the quantum state of a qubit. This is where things get really clever. Now, let's suppose the qubit is in the state 0 ket.
Okay.
A 393 nanometers laser, which drives the transition between 4s1 half and 4p1 half, will excite the qubit to the auxiliary p1 half state. However, this state is short-lived and will quickly decay back to the 0 state, emitting light in the
Right.
process.
Oh,
This
nice.
fluorescence can then be detected. However, if the qubit is initially in the 1 state, the same laser will not activate the transition and no photon will be detected.
Right.
This bright or dark behavior provides a nearly perfect method for distinguishing between 0 and 1. If the qubit is in a superposition state of 0 and 1, the probability of detecting fluorescence reflects the relative amplitudes of the two states. By measuring it repeatedly, we can determine the probability distribution of states, revealing the qubit's quantum properties. Chapter 5. The DiVincenzo's criteria. In 2000, David DiVincenzo at IBM described 5 core criteria for implementing a quantum computer, along with 2 additional requirements for quantum communication. These 5 are especially relevant here. The first criterion calls for a scalable system of well-defined qubits, which trapped ions provide in the form of linear or even 2-dimensional arrays of ions. The second requires long coherence times, something ions achieve by virtue of their near isolation from the environment. The third demands a universal set of gates, and in trapped ions, single qubit rotations and 2-qubit entangling gates can be performed with high fidelity using precisely tuned lasers and sideband transitions. The fourth requires that the qubits be initialized in a known state, achieved here through sideband cooling and optical pumping. Lastly, the fifth criterion concerns the ability to measure the qubits with high accuracy, which is exactly what is done using fluorescence detection that distinguishes bright and dark states.
Yep.
When you take all of these points together, it becomes clear why so many research groups and companies are investing heavily in trapped ion quantum computers. These systems naturally satisfy DiVincenzo's essential criteria for a quantum computer, and in modern labs, they're achieving gates and measurement fidelities exceeding 99%. While there's still a long road ahead to scale these systems to thousands or even millions of qubits, the remarkable progress made so far positions trapped ion as one of the most promising platforms for the future of quantum technology. To wrap things up, enjoy this animation of trapped ion quantum computing technology, courtesy of the Georgia Tech Research Institute. Thank you for watching, and I'll see you in the next video.
Yeah, it was nice. It's kind of interesting. I guess I'll try to wait for the next video from Professor Nano. Professor Nano. That was a year ago. 2 months ago. Interesting. So I'll try to see if there was a follow-on video that goes into a little bit more detail. But yeah, that was pretty cool.